Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome to this talk. I'm Vittorio Ferrari and I run the Calvin Research Group at the University of Edinburgh. A little bit of it is still left in Zurich, but we are migrating. So today I want to talk about visual recognition, in particular object localization, which is one of the main tasks of my group. So let's have a first look at what can we do today or over the years. So things started to work in the 90s, finally, in recognizing specific objects, such as these beautiful toys, against no background and lots of training images. So that's, I would say, solved. Since 2002, there are 100% recognition rates there. Good job. We managed to do some visual recognition to work. Then later on, people said, well, you know, specific objects, exactly the same identical beer can, that's kind of boring. Can we do object categories? So all instances that you would associate with the same noun in language. So let's start with faces, which are obvious application and they have limited variability. And people have been banging up, and probably arguably since Viola and Jones 2001, things have been working very well. And I would say since 2005, we kind of reached a plafond, and the task is almost solved. This means more than 90% detection rate when the number of false positives per image you get is about 1 in 10. For me, that's a good point. Above 1 in 10 is not very useful. So faces, that's one class. It's always frontal, moderately boring. So then people moved on to something harder. This is a data set I had the pleasure to see worked on a lot in the last 5 years. The TTA shape classes. You start to have more categories. There are 5. They're all defined by shape, so you cannot rely on texture patches too much. It gets harder. Still, this data set was fixed viewpoint, and there was never occlusion. Then I would say that recently we finally come to the point where it can be considered solved, above 90% detection rate at 1 false positive every 10 images. So that's kudos to that as well. However, the true holy grail is fully unconstrained. Mixed viewpoints, occlusion, truncation, and many categories. So everybody's working now on the Pascal Visual Object Class Challenge. And I have taken the pleasure of going through the 2011 challenge results, and the best method, which is unpublished, very interesting. I hope the authors will make it available soon, gets below 50% detection rate at 1 false positive every 10 images. That's not solved, and far from it. So this fully unconstrained case typically gets better when you have more and more training examples. And another thing that we would like to get is more and more classes, hopefully getting into the famous 30,000 that Widerman promised us in the 80s. So in order to learn a good model that is able to achieve this performance, these days what you do is the following. You collect 1,000 examples about per category. You have people clicking bounding boxes on each example, because modern detectors, they need a bounding box annotation to train. And you repeat this for many viewpoints and for 10,000 categories, and after 100 million clicks, you're done. So of course, nobody did that yet, fortunately, otherwise I'll be out of business. Manual annotation is very time-consuming. And even if we could do it, and some people argue we could, by Mechanical Turk, maybe Microsoft gives us a nice clicking grant. But even if we would do that, it would be incredibly boring, and we would not have learned anything. Like, maybe accept us to distribute money to the third world or something. We would like to do something humans can do, which is learn without clicking, at least after a certain child period where they train themselves. So in fact, that's the main goal of my research group, to try to reduce the amount of supervision that it takes to learn object detectors. And today I'm going to try to give an overview of 3 of our recent works. They're all future works, so in this sense I'm looking at the future, 3 months ahead, all at CVPR. And we try to exploit other indirect sources of supervision rather than humans clicking. And in the first work, this supervision will come from the motion that's observable in a video. We're going to look for YouTube videos, which maybe would be more suitable for Google than Microsoft. Another source of supervision is trying to exploit the semantic relatedness in classes that are organized in a hierarchy. And a third thing you can do is to try to learn multiple classes jointly in images annotated by which classes appear. So let's start from object detections in video. So as I said, this is the current way of doing things. Lots of training images with bounding boxes, and you got an object detector model. What we try to do is to train it from video. The big promise of video is that it is easier to segment the object from the background than in static images, because typically it moves different than the background. And that replaces the bounding box. And that's what we worked on so far. Another big promise would be that a video shows a range of viewpoints. So it's easier to build a multi-view model that from separate images. And of course, there is lots of evidence in studies of the brain itself, but also in development studies of children that object motion helps a lot in learning vision. So there are many challenges. Well, where do you find the videos? That's a big one. Once you found the videos, how do you detect the object of interest in there without human annotation? How do you put it in correspondence between videos? Then how can you learn a class model that is learned from video but performs well on still images? Because what we want in the end is beat the Pascal challenge, right? And that's still images. Can you learn from video and detect in still images? That's a big task. So here is an overview of the pipeline. We got our training videos, and we want to get an object detector. So the first thing we are going to do is to try to exploit motion segmentation to propose some candidate spatiotemporal tubes that go through the video. Some of them will be on objects. Some of them will be on the background, partially on objects. Then we are going to try to select one tube for each video, so that hopefully joint selection will get those tubes that are on the objects. Then we are going to sample some frames and train an object detector. So that would be a pipeline that's purely on video. However, what I am interested especially in is mixing the training data from the video with training data from still images from Pascal in order to get a better object detector from the two sources. And here is some of the videos in our database for 10 classes from Pascal. There are 10 classes that move. So potted plants and sofas, boring. Birds and cats, fun. That's what we do. We collect about 500 shots for each class, and we partition the video into shots. So you can see it's highly variable. Especially cats, they like to roll around a lot, at least cats that are filmed. Maybe sitting cats are not so filmable. So the first thing we do is to do point tracking and motion segmentation with the method of Sundaram and Brox, which is very recent, very nice. Basically, it's long-term optical flow that goes beyond 2 frames. And for videos like this one, where you have a very clear, very funny jumping cat with a clearly different background, the object's very big, it works very well. However, you can also have videos like this. Cows tend to be a lot lazier than cats, at least when filmed, and they hang around very slowly, and then they don't get segmented. So we have to manage to work with this kind of data. Once you have these motion segments, you can then fit a spatiotemporal bounding box, which we call a tube. We can do some robust statistics to avoid points that are moving substantially different than the rest of the segment, to be a little bit more robust. And you get these candidate tubes, we call them. So which one is the cat? Well, from a single video, it's going to be very difficult. Why not the little thing being the cat? But fortunately, we have many videos. And that's where the smart part of the work comes in. So the task will be to select one candidate tube for each shot in the videos so that a certain energy function is minimized. And this energy function can be visualized in this graphical model form, where every node represents a shot. The gray nodes are observed, and they represent the image features you observe in the tubes. And these bigger bubbles are latent variables that represent which of the shot in the tube in the video you pick. So these are integers that go from 1 to the number of candidate tubes in the shot. And if we look at the terms of this function we made, you have unary potentials that basically operate within a single tube, and they try to evaluate whether the tube is self-consistent, attracts a single object, so its appearance is homogeneous in time. It tries to also have it more in the middle of the image and elsewhere. And it also has a term that steers the selection process to objects rather than background. This is a work that we did, CVPR 2010, that I advertised it a lot of times. Basically, it's a general measure that measures the appearance of a window as to how likely it is to contain an object with a closed boundary and different appearance than the background. In general, class generic. This is other work. So the unary potential alone tries to prefer certain tubes over others on their own. But a very interesting potential is the pairwise one, which compares two tubes in different shots and looks how similar they are. This makes a lot of sense because you are operating within a single class, so all airplanes should look somewhat similar, whereas hopefully their backgrounds look more different. So if you want to minimize this combination of unary and pairwise potentials, hopefully you get one tube per shot so that they look somewhat similar, the selected ones, and they are appearance consistent and objects. Because we have a fully connected graphical model, we optimize it approximately with reiterated message passing by Kolmogorov and company. So this gives you a very nice approximate solution. So here are some results of this selection process. To the left, you see the motion segments, pretty bird. And in the middle, you see all the candidate tubes, and to the right, the one that was selected by our process. Remember, it has seen many birds in parallel. It didn't select it only on this one. You can see sometimes objects move very little, sometimes like the motorcycle, they move a lot, sometimes even go beyond occlusions. These are all the cases where it works very nicely because there is one tube that's on the object. If there is, normally picks it. But there isn't always. Actually, our results indicate that there is less than half the time. Sometimes there is this over-segmentation phenomena where the wheel of the motorbike is taken. I think my laptop is struggling to follow these videos.
The pairwise potential
yes.
for appearance.
Yes.
Can you just tell us a little more what, I guess it's not pixel-wise.
No, I was trying to give an overview, but sure, I can give you more detail. Sure. So what we do there, we sample a fixed number of frames on the tube, let's say 20 per tube. Inside there, we compute hog, bag of surf, or bag of sift if you like, and color histograms. And then we compare every pair of frames between two tubes, take the max of each, and learn the weighting between these different appearance cues. So rather standard. OK, this doesn't move very much, which is about the point. I think my laptop got my punchline better than me. This horse doesn't move. And so you don't get a motion segment. And then it fails. Then you can sample, once you selected tubes, you can sample some frames out of them and use them for training. So here, you have a pipeline that makes some sense, I hope. And you can try to see how well it does. You use the Pascal 2007 test set, which is the latest one for which you have test data available, and you can play around. And you use the standard evaluation protocol, so you only count a detection as correct if it overlaps tightly with the object, more than 50% intersection over union. As we said, we focus on objects that move. Sofas and potted plants are boring and also very difficult. And here you can see some, just focus on the last column. You can see what happens if you train Felsen-Zolmer-Ramanan deformable part model, which is currently one of the best working. You train it from standard still image data, it does about this performance. If you train it from our automatic pipeline, it does about half. But what is interesting is, what would happen if instead of using my automatic pipeline, I went and labeled every frame of the video, well, 100 per video, and manually clicked on bounding boxes? So the best possible case for video. Well, performance is still floating over there at the same spot. So this is good news. It means our automatic pipeline does close to the best you can on video. But the bad news is, wow, why is video so much worse than still images for a comparable same amount of training data in terms of frame? This shocked us for a while. We were thinking, maybe we should stop and not publish a CVPR after all. Then we thought, now let's try to mix the data. But first, we got to go to the bottom of this issue. Why is this so bad? And in fact, we discovered by inspection that we face a domain adaptation problem. The quality of the video frames is substantially lower than that of the images. Still images are better in terms that their gradients are a lot sharper. You can see there, well, maybe on this display you don't see it so well, but the video will be a lot more blurry on the edges. And it has compression artifacts that's a lot heavier, at least on YouTube videos. And to prove this, we collected certain manually annotated bounding boxes and computed the average strength of the gradients in there. And then we ranked them by strongest to weakest gradient. And you can see Pascal images are a lot sharper. A lot sharper. Then we also found a fantastic paper I recommend to everyone. One of the best papers in recognition. There is no novelty there, but it's fun. Soralba and Efros and Bias look at dataset bias, where they said, what are we doing? Let's try to train an airplane detector on video and test it. No, I'm wrong. Let's train a generic detector to distinguish video from still images. Can we do that? Class independent, just tell me if it's a video frame or an image. And you can. With standard features, you get to 83% accuracy. That's bad. And that really tells you that the two are different domains. So we need to do something to try to bridge between the two domains. And there are, maybe I don't go too much in details, but there are many standard methods that you can find in a fantastic paper by Haldomé III, which also has a very nice name, this guy. And some of the standard methods are, for example, the prior method is the most common in computer vision. You train a classifier on one domain, the source, and then you use it as a prior to bias the parameter of your target classifier. And that steers the target to the source and helps you to communicate between the domains. Or linint, which is the one that works best for us, you can train a classifier separately on target and source domains, and then linearly weight their output on the task domain in order to keep them together.
I guess the world has a lot of HD video.
The world has world has many HD videos which we couldn't so easily download, but maybe one day things will get better. We didn't try that, so this is an argument on YouTube videos. So here are some experiments with this domain adaptation where we tried to fuse the training data, the still image, high quality, and the automatically discover low quality video. We tried to fuse them together, bridging with these domain adaptation techniques. And this is a lot of numbers. But what the message is that if you try these standard approaches, so the approach all is mix all the training data, pred and prior are these domain adaptation techniques, you always get negative transfer. Basically, a single learned model gets confused by the different distribution in video and still images, and you actually do worse when adding video. We were really desperate at that point. And then finally, we found this lean-in technique, which sidestepped the issue because it trains separate detectors and only mixes them at the end. And that one gives an improvement. What you see, these are all deltas with respect to the best model of Felsen-Zolp on the VOC training data. So above 0 is good. At 0, it means video didn't help. And we never have negative transfer. We never have values below 0. And you get a 2% MAP improvement over half the classes. So here are some examples of what happens when you train a detector on only on still images, only on video, and then the combination. And typically, they help each other to refine position. And sometimes you get amazing phenomena like they are both completely wrong, but when they work together, they get a cut. So it is possible to improve state-of-the-art detectors by having videos just thrown in without any human annotation. So that, for us, was a good news. So now we'll talk about knowledge transfer on a hierarchy, which is a second way to try to get rid of manual supervision. There is this fantastic data set by Fei Li and others at Stanford called ImageNet. Did you all hear of it? Maybe you should ask the reverse, but. So basically here you have 16 million images over 15,000 or 16,000 categories organized by parent-child relations. So aircrafts are parents of airplanes and airliners. Some classes have a few images annotated by bounding boxes. About 5% of all images have bounding boxes. So a lot of room for us to try to do better. If we had bounding box on objects for all the images, we could train object detectors and solve computer vision, win Nobel Prizes, stuff like that. But we can't. So the purpose of our work is to try to exploit those classes that do have bounding boxes in order to transfer knowledge to the classes which do not, to populate these target classes with bounding boxes. Our dream is that one day we will have 16 million accurate bounding boxes. And we are not there yet. Don't hold your breath. And so these are some examples automatic. So it's not transferring knowledge from the sources to the target classes. So the overview we have is that we are going to consider for one target class, say this one, we are going to consider its siblings, so other aircrafts, and ancestors, which are all the classes above it, until the root of ImageNet. We are going to consider them as the sources if they have bounding boxes. And we are going to transfer 3 types of knowledge, location, appearance, and context. I'm going to go over that, and then combine them together. And the general scheme is that you go on a pair of knowledge source and type, and you learn a model for it. And then you can use this model to evaluate every window on your target image which don't have a box, and you obtain a window distribution, which basically captures an uncertainty of where the object could be in that image. And then we are going to use this to drive the selection of a bounding box for that image. So the first type of knowledge we transfer is location. We are going to basically take the source class, which has bounding boxes, and learn a KDE distribution over 4D. And then you can use this KDE to evaluate the windows, and you get something that's not very informative, but it's kind of better than all of the window in the image. So this should be 4-dimensional, but I displayed it in 2D here. Then a very useful type of transfer is to transfer the appearance of the siblings. So siblings are very related, obviously, because they're siblings, especially in ImageNet. You have a transporter van as opposed to a police van, so it's quite similar. You can learn an appearance model for it, say a chi-square SVM on bag of words. And then you can use it to evaluate all your windows, and you get a tight distribution. Another thing you can do is transfer appearance from ancestors instead of from siblings. And for this, basically, because we go back to ancestors till the root of the ImageNet tree, we use our object network, which I described before, that tries to separate arbitrary objects from their backgrounds, not class-specific. And this gives you a more broad distribution, but still on the object. You can also try to transfer context. I think this is a particularly fun idea. We might believe that sibling classes look similar. But in fact, the background they stand against, it looks more similar. So my argument is always cows and horses kind of look alike, but the grass they stand against, it's always exactly grass. And in fact, if you engineer your way through, you can make a context model that captures only the background. And the way we do this is to cluster background windows in the source class into background prototypes, and then measure how close positive windows are to the background prototypes to learn thresholds that say beyond this value in appearance space, you are below this value, you're pretty sure to be a background patch. Then you can use this again to evaluate windows in the test image. So now you've got a lot of window distributions. They all kind of give you a probabilistic opinion of where the object is. We've got to integrate them all. The way we do this is a log linear model where we weight the log probabilities by certain weights alpha. And the best alphas you can ever design to find are those alphas so that the combined distribution has a maximum, as a mode, which is most accurately localized on the object. But of course, you don't know where the object is, because that's it. So you have to train it on some other part of the tree in ImageNet where you do have bounding boxes. So we do all this cross-validation all the time. So this function, if you try to maximize it, it's tricky, because you need to find the parameters so that the maximum of the distribution is good. So that's hard to work out. But if you replace this argmax with a softmax, then you get a differential objective, which you can do gradient descent onto. And then you get optimal weights for the task of localization. And then to conclude, once you select one window per image on these target images for one class, you can then use these localized windows to train an appearance model which is for the target, so for the police van. You can use it to add it to the combined distribution and improve things iteratively. This is a good thing to do. It's done in many works, but in this scheme, it's linear in the number of images of the class as opposed to quadratic in our previous work in ECCV, which allows you to do it on a large scale. So here are some results. We try to be as large as possible. We took 219 target classes. They do have bounding boxes, although we pretend they don't. We keep the bounding boxes only a few. They only have maybe 100 out of 1,000, but we don't use them. We use them for evaluation, because we need to know how well we are doing, right? So we took on purpose some classes which have just a few bounding boxes and put them in the freezer, never look at them, just for evaluation. The siblings also have bounding boxes, and those we do use for transfer. In total, we have 500,000 images we work on. Only 12% of them have bounding boxes, which we do not look at. And then we evaluate Pascal intersection over union, this hard criteria of localization, averaged over everything. And these are a lot of numbers, of course. But what the message here is that we tried all combinations of source, sibling ancestor, and type of knowledge. And with this particular type of training of the alpha parameters, every combination improves over all its components, which is quite pleasing. And what one sees is that objectness alone is already doing quite well. It's already around 50. But if you integrate all the cues, you get a lot higher. And also, if you exploit an appearance model which is for the target class, learn on the fly, you go even better. And not surprisingly, Bagosov chi-square is the best appearance cue. I want to conclude by showing you some actual results, which are quite informative, I think, on this scale. We are not aware of previous works that tried object localization on 500,000 images. So it's quite interesting to see what happens if you ask the software, give me random results. You can no longer look at them yourself. And the first row is a classic result. It's a classic situation in ImageNet. The object is quite centered, occupies half the image, and we get it right. But our method also can find very small objects, like the candle next to this lady or this soccer ball next to the dog. And more interesting even is when you fail, what happens? Some images are so ill-posed, like here there are many balloons. Which one is with the ground truth annotated. It's completely arbitrary. Our method found a balloon, but maybe it's not the right one. Also, sometimes it finds groups of animals that correspond to the concept, but they are not one animal. And my favorite example is this image is labeled basketball. And this guy is playing basketball. It's not so bad, but it's not on the ball. And here are some more classic results where it finds the object halfway, but it's not very accurate. Here is a distribution over all the 62,000 boxes we could evaluate of the IOU result. And 55% may seem small, but in fact, the typical result is around 70%, which is very accurate for this measure. And many objects, we just don't find them at all. So the peak is in fact good enough, we believe, to train object detectors afterwards. So I would have had a third part, but I'll skip it, because with 25 minutes already, I'll just take questions. I think that's a better move in the interest of time. Thanks for your attention.
So Andrew had to go, so I'll take over. Okay.
Beautiful results. Quick question about both systems that you showed. Isn't there a bit of a self-fulfilling prophecy? Oh, sorry. Isn't there a bit of a self-fulfilling prophecy in that the tubes or the transfer is using measures of measures of color and appearance that are easy, and so the thing that you're able to find and you're able to learn and able to do then on the unlabeled data are the things that are sort of easy to segment already, right? So an object that changes appearance drastically over the course of a video won't have a satisfying tube and therefore will be rejected and not trained.
Okay, that's very interesting. So training appearance drastically can happen only if you switch on and off the lights or the object changes viewpoint, and the other viewpoints are extremely different appearance. In fact, I would argue that that's only partially a problem. In fact, I've shown you sequences with airplanes turning around. As long as the other videos also have airplanes turning around, there will be some viewpoints that match, and then the appearance cue, which is simple, like you argue, will be satisfied. So if you're comparing a car going to the right with a car going front, the two will not match well, and will probably not be selected unless the unary potential helps you. But because we have a variety of videos, it always happens that you have some of the viewpoints correspond between two videos, and there the appearance similarity function fires, which is also a maximization over all the viewpoints. So I didn't give all the details.
Do you keep tubes even if they're quite short? Or?
We keep all the tubes. Okay. We have like 20 per shot, and many of them are really absurdly small.
Cool, thank you.
Thanks.
Okay, so in your first work, you said that your performance, which was like of the detector which was trained on the video and evaluated on the still images, was not perfect. I think one of the good reasons for that could be that there is much higher variance in VOC dataset. Because if you train it, for example, from 1,000 samples but of the same object, then, for example, if you used color as a discriminative feature, you would train, for example, something from a red car, and then you would try it on some different car and it would not work because, one of the reasons is not really that it's not sufficient to have same amount of frames of the same object to train the detector. You just need different objects which are of the same class because you just don't capture that variant.
So
I think
that's a great question, actually, because it allows me to clarify things. In fact, what we trained this video detector from was all of the shots of a class that we downloaded from YouTube, not one object at the time. So the algorithm that does the selection already goes over all shots. There are about 500, and they typically contain maybe 50 to 100 different objects. There are many repetitions within a video, but not between videos. And the model that's trained on top of them is not color, but it's the standard Felsesop DPM model. So in fact, we have diversity. It's not one object at a time that's being trained. It's joint over the class. But still, your point, you still have a point, although I corrected the technique, because still, with the amount of video data we have, if we had with the same number of frames, they are distributed over about 10 times less different objects. So there are maybe 50 instances with many viewpoints instead of 500 instances. So there is an issue there. It's tough to collect so many diverse videos. That's an open issue.
So we are running out of time. There are a few questions, but we can probably take them over lunch. So let's thank Vito again.